Welcome back, everybody, and good morning to you. The topic this week is a discussion of diagram rules. And yesterday we looked at several examples. We set up the diagram rules, but we didn't reach the point where we were to discuss linked and unlinked diagrams. However, I would like to suggest a small change in program. So instead of diving into all the technicalities, we should also spend some time on discussing the second midterm, which is now available. And you can see down here at the end of the plans for this week, the link to the second midterm. Most of the material about diagrams, diagram rules, etc., is something which is well covered by chapters 5 and 6 of Shavit and Bartlett. And these diagram rules, which we are going to bring up again, as we discussed yesterday, these are essential when we now look at the midterm. Let me quickly bring up what we did yesterday. So what I'm going to do now is simply to bring back the whiteboard notes from yesterday. So let's take a closer look at them and bring back the diagram rules which we discussed yesterday with examples. And we are going to bring up some of these diagram rules and link them up with the second midterm. So the lecture today is going to rotate more around the second midterm because we are going to apply money-body perturbation theory to discussions of approximations to the ground state energy of a system. So let's go quickly back and look at the diagram rules. So if we now set up the diagram rules, the first one is to draw all topologically distinct diagrams by to a given order, where we link up particle and hole lines with different interaction vertices. And there are some specific restrictions then that the ordering of the interaction vertices is not altered. So if you look at that example which we had at the end of the lecture yesterday, it means that the order of these interaction vertices, which you see here, is not changed. So that means that this first interaction cannot replace that one. So we have this first interaction, then the second one, and the third one. So the order of this interaction is not something which we can change. Then the further constraints which we have when you have draw up all topological distinct diagrams is that particle lines and hole lines stay the same, which means that the contractions which we have performed are the same. So particle states remain as such, and same for hole states. And the ordering of the interactions at the beginning and at the end is also unchanged. So that means the Hamiltonian part which acts on the initial state and the Hamiltonian part which acts at the final state, which is the bra state. So the operations on the bra state and the ket states are left unchanged. With that, for each topologically distinct diagram, we would then set up the interaction vertices, and each interaction gives a specific element. So whether we have an interaction of this type, or we have a one-body operator, where O here just represents a given one-body operator, which we have to specify later. There is a factor here, which we just simply stated. That factor comes from the anti-commutation rules and the definitions of the contractions which we make. We will discuss that a little bit more in detail next week. So today, as I said, the focus will be more on the the second midterm. And then the same applies to the number of closed loops. We have also seen that when we act with the intermediate states, there will be a factor which is given by the sum over all the hole states minus the sum of the energies of the single particle states above the Fermi level. And that means for each interval between two successive vertices, we have such a factor. And then there is an additional factor which also follows from the contractions which we do. And when we looked at the second order diagram in perturbation theory, it was very easy to see what kind of contractions led to two equivalent pairs of lines which start and end at the same vertex. And then we sum freely over all the intermediate states. So these are basically the diagram rules. Now, before we dive into project number 2 or the second midterm, we are going to look at some further examples of the diagrams. And then when we've gone through these examples, we are going to go back to the second midterm. So let's bring back the whiteboard and look at further examples before we move back to the discussion of the midterm. So the midterm is essentially an application of many-body perturbation theory to a problem which we can diagonalize. That means we can apply full configuration interaction theory to a problem which reduces to a 6x6 matrix. And this is something which we can do. That will represent the exact answer. And with the exact answer, we can then look at approximations which come from perturbation theory. And because perturbation theory is nothing but an approximation to the exact solution. And in our case, we are going to have a case where we have a simple Hamiltonian, which we can perform FCI. So this midterm combines FCI theory with the Hartree-Fock. One thing which you will discover is that for Hartree-Fock theory, you don't need to make any calculations. So the problem which we have already has a Hartree-Fock basis. And this is something which you need to convince yourself about. So for the general discussions of the Hartree-Fock theory, you just need to bring back what you did in the first midterm. But what you will see is that you are already in a Hartree-Fock basis when you're setting up the equations. So that means that you don't need to perform a Hartree-Fock calculation. But that is something which you will see when you start solving the midterm. And when you have this, then the next step is actually to do many-body perturbation theory. And in a certain sense, this midterm it provides you also with a lot of the material for the final oral exam, which, as I suggested some time ago, is something which we could organize in the week which begins with Monday, the 16th of December. So if everybody's fine, we could settle down on Monday the 16th and Monday the 17th, no, Tuesday the 17th, as possible day for the final oral examination. So I will send you a detailed email about this a little bit later. But let's switch over to the whiteboard now and look at some examples. And then we are going to use that one to, these examples to link with the second midterm. So when we do many-body perturbation theory, we can obviously write down all the terms, order by order in perturbation theory. But when we do this diagrammatically, it can often lead to a deeper insight about the different contributions which arise. And also, it allows us to bring up a semi-kind of physical interpretation of different processes. So the example which we looked at yesterday was a typical example of a third order diagram, which you will encounter in the midterm as well. Now, let's look at some further examples here. So let's look at a new diagram to third order perturbation theory. So we're going to put labels here. So we have a whole line. We have a so-called Hartree-Fock contribution. And then we have a new interaction vertex, which now looks like this. And we have a whole state and a particle state. And then we are going to put labels on the diagram. So we label all the states, because what this is the result of is a result of a series of contractions. Now, we can now put labels A, and then we have a B here. And then we have a whole state I. We have a whole state J. and we have a whole state K here. So if we look at this specific contribution here, then we will have a whole state I here, and then we have a whole state which we can simply label as an L here. So in this particular case, what we see now is that we have, if we are calculating the number of whole states, we have 1, 2, 3, and 4. So that means that the number of whole states is equal to 4 here. Then, if we now look at the number of closed loops which we have, so we would now have one closed loop which comes from this term here, and then we have another closed loop which comes from this term. And then when we're looking at the closed loops, we need to look at the loops which start typically at one vertex and end at one vertex. So in this particular case, we would have one closed loop which is also represented by this term which you see here. So in this particular case, we do actually have the number of loops which is equal to 3. Then, if we look at the number of equivalent pairs, in this particular case, we have a whole line which begins here and ends there. And then we have similar whole line here. So these two whole lines represent a set of equivalent pairs which start at the same vertex and end at the same vertex. So that means that the number of equivalent pairs in this case is equal to 1/2. So if I now collect everything which I have, this diagram will have a -1 in front of it because we have 3 loops and 4 whole lines. We are going to have a factor of 1/2 due to the equivalent pairs. Then we need to set up the sum over the intermediate states. So we have an A and B, and then we have 4 whole lines, A, J, K, and L. And now we need also to set up the interaction matrix elements, which in our case is given by these 2 body contributions. And if we look at the first term, which is the one which we would say corresponds to the action from the bra state, we start on the top here, then we have now a outgoing whole line, I. We have similarly an outgoing whole line, K, on the right-hand side. We have an interaction vertex, and then we have an incoming particle state to the left, A, and then we have an incoming whole state, K, here. Then if we look at the intermediate interaction vertex here, we have one incoming whole line, I, and one incoming whole line, J, and one outgoing whole line, L, to the left, and one outgoing whole line, J. And then we have a interaction, and we have an incoming whole line, I, and then an incoming particle line, B. And then the final element contains now 2 outgoing whole line, A, B, the particle line, sorry, and then we have 2 whole lines, L and J. And I'm skipping the anti-symmetrized subscript because I'm assuming now by default that all of these contributions are represented by anti-symmetrized matrix elements. Or rather, it's more correct to call them integrals. But I use this sloppy naming matrix elements because I often store these integrals as matrices. So the energy denominator, which we need to add then, is now given by the sum over particle energies and subtracted from the number of whole energies, which, so we in this first energy denominator, we have then a whole state epsilon L plus epsilon J, and then we have to subtract epsilon A minus epsilon B here. If I then look at the next interaction vertex and the final one, then I have to look at the whole lines in between here. And in this case, I have simply epsilon I minus epsilon A. So that means that I have a new denominator, contribution to the denominator, which goes like epsilon I minus epsilon A. And that is the final contribution for this specific term in many-body theory. Now let's look at the diagram to 4 further, which is something which we will encounter when we now look at the many-body perturbation theory in the second midterm. So we can pick up a new contribution here, and let's now set up a diagram to 4 further, which is one of the diagrams you will get in the midterm, which will be non-zero. So in this case, we are going to look at the 2 whole lines, and then we are going to have particle states here. And then we put on labels. So we have A and B, and then we do C and D, and then we do E and F up here. And then we have an I and J here. So we put labels on the diagram. This is an example of a 2-particle state which is being propagated. And in this case, it's being propagated to a state AB. So we create here a 2-particle, 2-hole excitation. And then the whole states remain in the same single particle states. But what we do now is that we perform an excitations on the 2-particle states. So we move from AB to C and D, and then we go back to the final 2-particle, 2-hole state, which then gets annihilated by the interaction, and then we're back to the ground state. So if we now look at the number of whole lines which we have here, in this particular case, the number of whole lines are simply 2. The number of closed loops in this case is given by 2. So that means that the factor which we get from -1 of NL plus N holes is just equal to 1. Then, in this particular case, we also need to count the number of equivalent pairs. So in this particular case, we have these 2 whole states, I and J, which now gets created here, and they're propagated through this whole diagram. They start at the same vertex, and they end at the same vertex. So this gives us 1. And then, if we look at the states A and B, we have 2 particle states which get created at this vertex, and then they end at this vertex. So we have an addition to 1 here. And same with C and D. They get created at the same vertex and end at the same vertex, and same with E and F. So we are coming back to the derivation of that specific diagram rule. But if you go back to the diagram which we had to second order, it is pretty intuitive to see why this factor appears from the type of contractions which you're doing and the way we have defined the interaction matrix elements. So we get +1, so we actually have a factor of 4. So this means that we end up with 1/2 to the power of 4, which obviously is equal to 1 divided by 16. So when we now are collecting these terms here, this diagram is going to give us 1 divided by 16. There is a plus sign. And now we need to set up the summations of all the intermediate states. So we have the 2 whole states, I and J, and then we have A, B, C, D, E, and F. So this is almost like an exercise in setting up the alphabet. Then we start with I like to start with the top interaction. So that is the final interaction. Then we see that we have 2 outgoing whole states, I and J. And then we have 2 incoming particle states, E and F. If we go to the next interaction vertex, which is this one, we have 2 incoming particle states and 2 outgoing particle states. So this is an E and F. So that these states here result from one of those intermediate operators which we had, Q divided by the energy operator. And in that case, we picked out a Slater determinant which contains a two-particle, two-hole excitation, where the whole states stay the same, they are unchanged, and the only thing which changes are actually the two-particle states. So the second interaction piece is now given by CD, and then we have the next CD here, and then we have a V, and then we have a final AB here, and then we need to multiply this one with the final interaction matrix element, which is the one we started with, and then we have two outgoing particle lines and two incoming hole states. So these are the interaction vertices. Finally, when we then look at the energy denominators, we are now going to have three energy denominators. So there's going to be one here, and that is simply given by the sum over the whole states minus the sum over the particle states. That means their corresponding energies. So the first energy denominator, the one at the bottom, is going to give us epsilon I plus epsilon J minus epsilon A minus epsilon B. Then I'm looking at the next term here. In this case, I have the same whole lines. So the whole lines are just propagate through the whole diagram, which means that the two whole states are unchanged. Whereas what happens now is that the different particle holes, the particle states, can change from one term to the other one. So we end up with a new one, which is epsilon I plus epsilon J minus epsilon C minus epsilon D. So in every interaction vertex here, what we are doing is that we are propagating a two-particle, two-hole state, but where the two hole states stay unchanged. So this is, again, when you look at it, this is a two-particle, two-hole excitation, and this is the final one is also a two-particle, two-hole excitation. So let me just put a multiplication sign here and just do that one here. So that gives me an epsilon I plus an epsilon J minus epsilon E minus epsilon F. And that is our final diagram here. So let us now also look at some other contributions which we can get. Let's go back to the second order contribution and just make sure that we get the same contribution which we got when we calculated everything analytically by setting up all possible contractions. So when we look at the second order diagram, we had a diagram which represented a one particle, one hole excitation. So one of the things which we discussed to second order was the fact that to second order, we end up only with diagrams which represent either one particle, one hole, or a two particle, two hole excitation. These are the only possibilities which we could produce to second order perturbation theory. So one of the diagrams which we ended up drawing then was a diagram of this type. And in this case, what we have now is a particle state A, we have a whole state I, we have a whole state K, and we have a whole state J here. Now, in this particular case, what we have now is that the number of hole lines is equal to 3. The number of loops is also 3, closed loop. We have this is a closed loop, this is a closed loop, and this is also a closed loop. So that means that we have n loops equal to 3. So that is going to give us a factor of +1. Also, we have the number of equivalent pairs in this case is equal to 0. So there is no equivalent pair here because we don't have the same whole line, pairs of whole lines which start at the same interaction and end at the same interaction. So that means that in this particular case, when we set up the final expression, we are going simply to have a factor of plus, and then we sum over the intermediate states. So this is I, J, K. And then again, if we start with the top vertex, we have an outgoing whole state I to the left and an outgoing whole state K to the right. And then we have V, and then we have A and the incoming whole state K. And then finally, we have the lower interaction where we have an outgoing whole line A, an outgoing whole line J, and then we have a incoming hole state I and an incoming hole state J. And then we have the energy denominator now, which is simply the difference in energies between the number of hole states and the number of particle states. So that means in this case, we get back what we had when we calculated everything analytically by doing the contractions. So using the diagram rules is a very powerful way to actually look at many-body contributions to a given order. So this is a kind of established practice in many-body perturbation theory, and also in copper cluster theory, which we will start discussing next week when we have done the formalities with some of the derivations of the diagram rules. So if we now look at the final example, which is also linked with the second midterm, let us look at a diagram to fourth order in many-body perturbation theory. And now I'm going to try to draw this properly. And I'm going to draw it more like this. So these are the interaction vertices. So I'm going to have a whole line here. And I'm going to have a whole line here. And then I'm also going to set up a whole line here and a whole line here. But then I'm going to have the particle lines going in here. And then I have a new particle line coming in here. And then finally, I have to link this to the final vertex, which we have here. And this is a particle state. Now I'm going to put labels on it. So there are many ways of drawing these diagrams. Remember now that you can permute these interaction vertices. That means that you can obviously change the order of the whole lines here. We can take exchange contributions. We cannot change the order of the interaction. So this is the one which we start with. So you can think of the Hamiltonian acting on the ground state. And then we have some intermediate excitations, which in this particular case, if you now look at the intermediate state here, this one, so let's mark it with red. Because when you look at this particular state, this represents what we will call a four-particle, four-hole excitation. Because if you now count the number of single particle states you have here, you have four whole lines and you have four particle states. So this represents an intermediate excitations of a four-particle, four-hole type. This is a feature in many-body perturbation theory, which you will see when you look at different orders, that every order introduces a specific particle hole excitation. So in this particular case, when we go to fourth order, we find an explicit four-particle, four-hole excitation. Actually, this diagram is one of the few ones which will be allowed in the second midterm as a fourth order contribution to perturbation theory. So perturbation theory is something which allows you to include higher and higher order contributions. So every order then introduces a specific contribution to that specific order. So when you were to diagonalize a many-body system, like the one which we have in the midterms, where we are going to look at four particles, in the second midterm, we can produce at most four-particle, four-hole excitations. But when you diagonalize, you sum these excitations to infinite order. So when you diagonalize, you will have all possible four-particle, four-hole excitations. When you do many-body perturbation theory, on the other hand, these contributions will appear order by order. So when you go, for instance, to sixth order, there will be sixth order four-particle, four-hole excitations. When you go to, for instance, 20th order, there will be a 20th order in the interaction. Remember now that we are making a Taylor expansion in terms of the interaction divided by the energy denominators. So to 20th order in interaction, there will also be 4-particle, 4-hole excitations. So this is also one of the reasons why many-body perturbation theory is such a powerful method, because it allows you to give this kind of physical interpretation to different diagrams here. You would actually get this if you were to look at the intermediate states. So every intermediate state which you see here is the result of this operator Q divided by this energy operator E0. So let's now put labels on this diagram here. This is one of the diagrams you will end up having to calculate in the second midterm. So now we put labels. So we have an I, and then we're going to put a J here. We're going to put a K here, and then we have a final state L here. And then we put labels on the particle states. So this is going to be A, this is going to be B, and this is going to be C and D. Now again, we calculate the number of hole lines, and in the number of hole lines in this particular case is given by 4. So n holes is equal to 4. Now, in this particular diagram, we don't have a closed loop. So the number of loops here is actually given by 0. So in total, this is going to give us a +1 as a sign in front of the diagram. Now, if we look also more carefully here, if we think of equivalent pairs, in this particular case, what we are going to have is obviously this I and J and L here. That gives rise to an equivalent pair. We have the particle states A and B, which start at the same vertex, this one, and end at the same vertex. Similarly, we have C and D here, which start at the same vertex and end at the same vertex. And finally, we have the whole pair, J and K here, where they start at the same vertex and end at the same vertex. So in this particular case, what we have is an n equivalent pairs, which is equal to 4. And that gives rise to a factor 1 divided by 16. Okay, so let us now look a little bit closer at the final expression which we're going to get for this diagram. So we will now have a summation of all the particle hole states. So the final expression is going to be given by 1 divided by 16. And then I have a sum over A, B, C, D. And then I have the whole states I, J, K, L. And now I start again with the top vertex. So if you look at the top vertex here, so let's go back, we would have an outgoing whole state I and an outgoing whole state L to the right, to the left and the right respectively. And we have an incoming particle state C and an incoming particle state D. So that means that this specific vertex has I and L and V, and then we have CD here. So let's now look at the second interaction vertex. So in that case, we have 2 outgoing hole states, J and K, and we have 2 incoming particle states, A and B. So that means that this specific term gives us now we had J and K, and V, and A and B. And then we look at the third interaction vertex. So for the third interaction vertex, we have 2 incoming hole states, J to the left and K to the right. And we have 2 outgoing particle states, C to the left and D to the right. So that means that we get then a new contribution here, which is C, D, and then we have V and J, K. And finally, we have the first interaction where we have an outgoing AB and an incoming IL. So that means that we get A, B, and then V, and then we have I and L here. So these are the interaction matrix elements. And then we have the energy denominator. So let's put a multiplication sign again here. We're going to have 3 energy denominators. So let's look at the first one, which is this one. So you see we have A and B as particle states and I and L as whole states. So that means that I'm going to get a denominator where I have an epsilon I plus an epsilon L minus epsilon A minus epsilon B. By the way, my A here looks like a D, so let me just correct this one. So this is A and B. So my A looked like a D there. Sorry for that. So let's now go to the next case, which we have. So the next case is actually this one. And here you see that we are going to have the single particle energies, which will correspond to a 4-particle 4-hole excitation. So now we need to collect all the whole states, which you have here, and then all the particle states. So that intermediate state here is now reflected in the energy denominator. So we are going to have epsilon I plus epsilon J plus epsilon K plus epsilon L minus epsilon A minus epsilon B minus epsilon C minus epsilon D. And finally, the last one, which is the final gap between the 2 last vertices, which is this one. And here we have the whole states I and L and the particle states C and D. So the final one is just going to give us epsilon I plus epsilon L minus epsilon C minus epsilon D. And that is the final contribution from this specific diagram. Now, what I wanted to do now is actually to bring us over to the second midterm and the kind of model which we are going to look at. Because that will link with some of these examples which you're going to see here. So let's take a look at the specific system which we're going to have in the second midterm. So in the second midterm, we are going to look at a system which is driven by a pairing Hamiltonian. So a pairing Hamiltonian acts only on pairs of particles which are on the same single particle level. So we are going to define a system which has n equal to 8 single particle states. But these single particle states are going to be doubly degenerate. So that means that when we look at the system here, we are going to have 4 particles which then can be placed in these single particle slots. So that means that what we are going to see then is a system where we have 4 different slots, and with 4 particles, we can then make an ansatz where the ground state is given by 4 particles filling the lowest single particle states. So the Fermi level is defined by this one, and we are going to put labels on every single particle state. So this P here is equal to 1. This P is equal to 2 here. And then we have a P equal to 3. So this labels these single particle states which are degenerate, and they have a degeneracy, which I label for D, which is equal to 2. So that means that we can have 1 with spin up and 1 with spin down. Then we have the next one with spin up and spin down. Now, this is a system which we are going to constrain. As you will see, the Hamiltonian, when you start looking at it, it's going to be a Hamiltonian which is going to commute. This is part of the exercises. So the Hamiltonian will commute with a spin projection, and it will also commute with the spin operator equal to 0. And this SZ here is now going to represent the projection of the total spin. on the z-axis. So in our case, this z here is going to be the total spin of the system. So it's not a single particle spin, but we are going to constrain it to cases where this one is equal to 0. And we are also going to limit ourselves to a case with no broken pair. Because the Hamiltonian, which we are going to design, which is called a pairing Hamiltonian, is a Hamiltonian which now acts only on pairs of particles with opposite spins. So that means that the only possible states we are going to look at now, when we have constrained the total spin projection to be 0, and we have a Hamiltonian which is not allowed to break pairs, then we are going to constrain ourselves to a system where the number of pairs is conserved, which means that we can only promote pairs to excited states. So let's take a closer look at this. It means that the possible states, when we now make this constraint, with that constraints, we're only going to get 6 possible Slater determinants. Now, one thing you will also see when you look at the basic properties of the Hamiltonian is that the Hamiltonian commutes with what we call the pair operator. So you can define, as you will see in the exercise, a pair operator which creates or destroys a pair. And that means that we are going to have a Hamiltonian which will conserve the number of pairs, and it will also conserve the total spin projection and the total spin value. So these are properties of the Hamiltonians which are conserved symmetries, which will allow us to simplify the many-body problem. Because when we look at the problem which we have in the project, so we would have the number of configurations, which should then correspond to all the possible Slater determinants which we can make. So the number of configurations is going to be given by n divided by, with n the binomial factor, and this gives us n factorial divided by n minus n factorial times n factorial here. And this will give us in total 70 many-body states. However, when we break it down in this type of symmetries, because the Hamiltonian commutes with specific operators, then we can set up the total Hamiltonian to diagonalize, which would be, if we do this in a brute force way, it will simply be a 70 by 70 Hamiltonian, but we can break it down into blocks due to specific symmetries. And the first block which we are going to look at is the one with a spin projection equal to 0, a total spin equal to 0, and no broken pairs. So when we look at this system at hand, we are going to have a set of Slater determinants. If we go back here, we are going to label this one as our ansatz for the ground state. This will be our phi 0. In a certain sense, this mimics what you did in the first midterm, where you looked at the ground state for the helium atom and the beryllium atom, and you looked at possible one particle, one hole excitations. Now, in our case, we are going to limit ourselves to a specific type of excitations, which we are going to call pair excitations. Now, in nuclear physics, for instance, this type of interaction make a very good approximations, first order approximations to the nuclear Hamiltonian, because in nuclear physics, there are strong pairing correlations due to the short range part of the nuclear force. Now, this type of pairing model was also used by Badin, Cooper, and Schrieffer when they made the first model for superconductivity, for which they got the Nobel Prize. So it's a model which is widely popular in physics because pairing correlations can play an important role in many body systems. You can actually take a general Hamiltonian and rewrite it in terms of pairing correlations plus other types of excitations or correlations, as we call them, and then simply isolate the pairing part and neglect all the other ones. So you can actually rewrite a two-body interactions in second quantization in terms of one part which contains just a specific set of correlations plus all the rest. This is something which we could discuss if you're interested more on a one-to-one level. Okay, so let's take a small break before we continue our discussion of the second midterm here and the basic physics and the model which we are going to look at. So what we want to do in these two lectures is to link the practical aspects of setting up contributions to perturbation theory order by order with this specific example which we have from the second midterm. Now, just to quickly repeat, we are going to limit the set of states which we are going to consider to states which conserve the number of pairs. So in our case, we are going to have two pairs. We are not going to allow broken pairs. In the midterm, you're going to study properties of the Hamiltonians. And one of these properties is that the Hamiltonian commutes with the spin projection operator. That means that the total value of the spin projection, which you see in this case is a spin up plus a spin down, 0, plus a spin up plus a spin down equals at the end to a total spin equal to 0. So we want to keep that specific symmetry, and also we want to keep the number of pairs conserved. So this Hamiltonian here, which we have in the second midterm, that commutes also with the operator which considers the number of pairs. So we're going to define, as you will see in the midterm, an operator which creates a pair and destroys a pair, which means that the Hamiltonian, as you will show in the midterm, we are not going to discuss this here in the lecture. You will have to show that in the preliminary exercises, that the Hamiltonian commutes with the pair operator as well. So that means that when we now look at the specific system which we have now defined, so no broken pairs and the total spin projection equal to 0, it means that there are only 6 possible Slater determinants or configurations which we can make. So the first one is obviously our ansatz for the ground state, phi 0. We have the Fermi level here. And then we can now perform excitations of pairs because we don't allow a pair to be broken. This is going to have quite some consequences for us when we are setting up the diagrams which can contribute. And we will look at examples of that after we have discussed all the possible Slater determinants which we can make. So let us now just simply do the combinatorics and distribute two pairs in 4 levels, 4 doubly degenerate levels, which means that you now can reduce this problem which we had here, which was given by n equal 8 and 4. We can then think of n as the number of levels which the pairs can occupy. So n becomes 4, and then the number of pairs is simply 2. And then the combinatorics is going to give us 6 possible Slater determinants. So let's simply list them then, and then look at how we can define them in terms of particle hole excitations. So the thing which we simply do now is to just list these other possible states. So the labeling here is just random in the sense that I'm taking this one as the first 2-particle 2-hole excitation. So we have a p equal 1, a p equal 2, p equal 3, and p equal 4 here. So we preserve the spins. So the first one is a spin up, the second is a spin down, and then we have a spin up and spin down. So this has a total spin projection equal to obviously 0, because we sum the single spins. So the total spin projection is actually the sum from I equal 1 up to 4, the particles which we have, and then we simply sum the individual spin values, which can either be minus a half or plus a half. So in our specific case, this is always going to be conserved and equal to 0. Now, obviously, we could have had a situation like this one, where we also have the same spin projection, but here we break a pair. So this is a case which would not be allowed by the Hamiltonian if we just consider the no broken pair case. So it's a state which is allowed, but it is a state which, when we put the restriction that we are looking at number of pairs being conserved, and the Hamiltonian actually commutes with a pair operator, that means that this state here is not possible if number of pairs is conserved, if no broken pairs. But it is a possible excitation among the 70 which we have here. You can quickly see that if you take the transition probability with this specific state, which you have here, and a state like this one, you would find that transition probability to be equal to 0 for the Hamiltonian, which has from the interaction part of the Hamiltonian. So that means that the states which we are going to have are going to simplify. So let's just keep drawing them. So if we leave the whole states here, we could now have another two-particle, two-hole excitation. So both of these are what we call two-particle, two-hole excitations. I'm just going to draw the spin states here, and I skip the labels P1, 2, 3, 4. So this is another, both of these are two-particle, two-hole excitations. And we label this one as a phi 2. And then you see the system here is pretty obvious what kind of states we should get. So let's just draw this without putting any labels. So we can now have an excitation of the two lowest one up here. This is also another two-particle, two-hole state, which we simply label as a phi. So we had phi 1 here, and we have phi 2, and we simply call this phi 3. And then we have a new one. And as I said, I'm skipping both the spins and the labels on the single particle states, which are doubly degenerate. And then finally, we have this one as well. This is also a two-particle, two-hole excitation. And we label this as a phi 4. And then it shouldn't come as a surprise that the final possibility is just the one which you see here. And this is a four-particle, four-hole excitation. And this is a phi 5 here. So these are the states which we are going to have. Since we don't allow breaking of pairs, there is no one-particle, one-hole excitation, because the state which you see here, this one here, you could have had a different one, which could be something which looks like this. So we could have these states remaining, but then we could allow this one to be excited. And that state which you see there, this is an explicit one-particle, one-hole excitation, which is also not included in the case when we don't allow for any broken pairs. It still has a spin, a total spin projection, which is equal to 0. So if we only considered spin, then we would have a much bigger block of Slater determinants when we are going to diagonalize. However, since the Hamiltonian also commutes with the pair operator, so the number of pairs is a conserved quantity, then these states which you see here, which we have defined now, they set up their own block of states. And when we calculate the matrix elements between this state here And this state here, for the interaction itself, that is going to be equal to 0. Okay, so with that, we can now start making a link with the FCI. And you see that in the FCI case, what we will get then is a Hamiltonian matrix, which I'm now just setting up without putting in numbers, because you will have to put in the analytical expressions. But the FCI Hamiltonian matrix is now going to look like as follows. So I'm going to have a 6x6 matrix when I have total spin equal to 0 and no broken pairs for that specific model which we have with 4 particles. So there's going to be the phi 0 elements. I will have the phi 1 here. I will obviously have phi 2. I will have phi 3, phi 4, and phi 5 here. And we can think of these as specific blocks. So let's just set up the matrix elements. And then I have a phi 1, I have a phi 2 here, I have a phi 3, a phi 4, and finally a phi of 5. So the first thing you would have to do after you've tested these basic properties of the Hamiltonian, that it commutes with the spin operator, with the spin projection, and also the pairing operator, is to set up the Hamiltonian matrix. Now, one thing which we know is that since we have now defined these states here to be 2-particle, 2-hole states, so the states in red here, they are 2-particle, 2-hole excitations. We know that this specific state here is a 0-particle, 0-hole excitation. So that's 0-particle, 0-hole. And the final state which we have here, this one, is actually a 4-particle, 4-hole excitation. So what we have here is a 4-particle, 4-hole excitation. So this one is a 4-particle, 4-hole. And we know that since this is just a 2-body, at the most Hamiltonian, we will have matrix elements X, which are different from 0. We will have X, 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 X here, but then we will have 0 here. So these matrix elements are 0. And because with 0-particle, 0-hole can only link with at most 2-particle, 2-hole excitations. So this is going to be 0. So what you will find then, if we now just set up the diagonals, so we will have diagonal elements which are going to be non-zero, and you have to find them because you're going to diagonalize the problem. But you will then also see that there will be states which will give rise to transition probabilities or matrix elements, as we call them, which are actually equal to 0. So let's now take a closer look here. So you see now that since you have a 2-body interaction, when I now link this state here, which has 4 different single particle states, with obviously the ground state, which I have here, then there is no single particle state, which is equal on the Bragg side and in the Ket side. So when you then are setting up, for instance, the calculations where you now look at this final state here interacting with some of the other states, then you will find that for some of these other states, they're going to be zeros. So what you need to do now is actually to find these different matrix elements. So in this specific case, when you have a phi 1 with phi 2, these are all going to be okay, but I'm going to leave a question mark here. So these are matrix elements which you will need to find in the exercise. I'm not going to give you all the answers here. But it's sometimes, instead of running the calculations, you can simply look at the different configurations you've made and try to figure out whether there will be a potential for an overlap or not. That means that there will be two-body matrix elements which will be non-zero due to the fact that there will be Slater determinants which have less than 4 particle states which differ. So you will typically see then, if you now look at this specific state here, this one, and you want to match that specific state. So you see now that now we have 2 states here in P2. And here I have a state in P4. If you now take the overlap between phi 4 and this specific state phi 2 here, no, not phi 2, this should be, yeah, I actually meant the state phi 1. If you look at this specific state here, this one, and you take the overlap between phi 4 and phi 1, you see now that phi 1 here has 2 single particle states in P1 and 2 single particle states in P3. So this is also an example, this case here is an example where you have 4 single particle states which are different in the ket side from the bra side here. So that means if you calculate the expectation value or the transition probability of the Hamiltonian with phi 1 and phi 4, that is also going to be 0. So you can actually see from the pictures which you make of the different states, which will give you a non-zero contribution and which will give you exactly 0 when you plug in the pairing interaction. So that's a very useful exercise to be done. And if you take phi 4 with phi 1, since the single particle piece is only going to act on the diagonal elements, it means that that specific matrix elements between phi 1 and phi 4 is going to be 0. So if you go back to this image here, and then we take away one of these, you will then see that the phi 4 and phi 1, that specific matrix element, which we have here, is going to be exactly equal to 0. So I actually want you to go through these different cases and then build up the full Hamiltonian matrix. Now, why do we insist on this? Now, the reason for that is that when we now go to many-body perturbation theory, there are going to be pretty many diagrams to a given order in perturbation theory. Now, the second order piece is pretty simple to evaluate, but when we go to third order, there are going to be diagrams which we need to be a little bit careful about. And that has to do with the type of excitations which we can make. So let me try to guide the eye a little bit. Now, the simplest case with these restrictions we have made, so no broken pairs, and the total spin projections equal to 0. If we now look at second order, so to second order perturbation theory, we had only 2 diagrams. We have this one, and then we have this diagram here. And I'm not putting labels on it. Now, this intermediate state which we have here is a 1 particle, 1 hole state. This one which we have here is a 2 particle, 2 hole state. So that means that in many-body perturbation theory, what we are going to get is, if we look at the 2 particle, 2 hole diagrams, this means that we have an excitation here. This could be a phi 0, and then I have HI, and then I have phi 1, and phi 1, for instance, of H. So we have a phi 1, and then with phi 0, divided by the energy denominator, which I just write like this now.
So if I do that, you see that this is a possible contribution because this specific matrix element, which we have here, is going to be non-zero with a pairing Hamiltonian. So for the two-particle, two-hole case, for that diagram, we will get contributions to second-order perturbation theory. So that this will be a diagram which explicitly contributes to the approximation to the exact diagonalization. So one thing which you will see is in the calculations here, since you are going to calculate this for different strengths of the interaction, you will see that when the interaction is weak, then second-order perturbation theory will actually give a good approximation to the full FCI calculation. So what we have to think now in this midterm is that many-body perturbation theory is just going to represent an approximation to the exact diagonalization. And what you will see is what you would expect, that if the interaction is weak and the gap between the single particle states above and below the Fermi level, if that is also big, then the many-body perturbation theory terms are going to be small, and perturbation theory gives a good approximation to the exact ground state and also other possible states if we were to consider states beyond the ground state. But this typical contribution here is something which you would have to set up, and you would also get contributions from the other states. So here you would have, in addition to these, you would have phi 2 contributing, you would also have phi 3 contributing, you would have phi 4, but not phi 5, because that represents a 4-particle 4-hole excitation. So if I stay to second order, that means that I would not include in my many-body perturbation theory approximation contributions beyond 2-particle 2-hole excitations. So if I go back to this Hamiltonian matrix, that means that to second-order perturbation theory, I will not have any 4-particle 4-hole contributions. However, if I go back to the examples we had before the break, there's going to be a diagram like this one, which represents to fourth order a 4-particle 4-hole excitation, which will be non-zero for this specific Hamiltonian. And that means that when you include a term to fourth order perturbation theory, you may, depending on the strength of the interaction, you may get closer to the exact diagonalization case, which includes a 4-particle 4-hole excitation. So these are the kind of things we want you to play around with and gain a deeper insight about the role between the strength for the interaction and the value of the single particle energies, which then defines the gap across the Fermi level. So to second-order perturbation theory, this diagram here is going to give you explicit contributions. And the Hamiltonian is so simple that you will be able to calculate analytical expressions for the second-order perturbation theory. So that's one of the tasks in the exercise. So I'm just trying to guide you through the kind of things you should get and the kind of interpretations you can make. And this is such a simple system that it allows you to build up an intuition by looking at the diagrams. And then from the Hamiltonian, which you have defined, you can simply tell by looking at diagrams which diagram will contribute or not. Now, this case which you see here is a 1-particle 1-hole excitation. And if we now go back to the full configuration interaction case, there is no 1-particle 1-hole excitation simply because we, by construction, have not allowed a state like this one. So the Hamiltonian commutes with a number of pairs and commutes with a spin projection, which means that that specific configuration is not allowed if we consider a case with no broken pairs. So that means that when you now look at this specific case here, what you would get is a specific excitation of this type here. So you could have the two remaining here, like that, and that would correspond to this one and that one. And then one of the states remains a whole state, So that means that if we think of this particular state here, we could now think of that remaining a whole state. So that means that we have a state here now, which stays as a whole state, but then we promote one of them up above the Fermi level. So that is a possible one particle, one hole excitation, but this is not allowed here because we are breaking a pair, even though the total spin projection is concerned. So the one particle, one hole diagram is going to give us a 0 contributions. So this does not contribute. When we then go to third order, there are going to be many more diagrams. So to third order, we can have diagrams of this type here, which we had before the break. So if we look at this diagram, this is also a diagram which we immediately can say does not contribute. The reason for that is that if we look at the first term, this is actually okay because that produces a two-particle, two-hole excitation. So we would say this is an okay excitation with no broken pairs. So a case which that would correspond to is that we go from the ground state, which we start with, and we go to an excited state, which now could be given by this possible configuration. So this is a state which we call for phi1. So this is our phi1. So this is a possible excitation which we have here. So this process here is now simply represented by us going from phi0. There is an interaction which acts on the state, and that brings us to the state phi1. So this is a possible excitation. However, when we now come to the next interaction vertex, what we are producing here is actually a one particle, one hole excitation. So that means that the phi1, which we put up here, would now go over to a state which could look like this. So I have this state here, but now I keep one of them here. It could still have total spin projection 0, but now I produce a one particle, one hole excitation, which now is slightly different, but we now have broken a pair here. So, no, sorry, this is not the correct state. Let me just rewrite it. So I can keep these two here. But now I change the whole state. So I could bring one of the particle states down here, and then I could have a state like this one. So where the particle state is there. And that means that what I get now is a one particle, one hole state, which is not included in the set of states which we had from phi0 up to phi5 here. So that is not going to be allowed because it's simply a one particle, one hole excitation. So the Hamiltonian which we have is not able to give you a matrix element which is non-zero. So this diagram here does not contribute. We can now look at another third order diagram, which you will find in the midterm. So if we look at this diagram, which we have here, one of the reasons why I always like this diagrammatic representation is simply because it allows us to extract immediately what type of excitations can take place. So if you look at this specific diagram, we produce a two-particle, two-hole excitation here. And that could be, again, this state phi1. So it could be a state which looks like this. So I'm dropping the spin degrees of freedom here. So this is a possible excitation which we make. But then what we are doing next now, when we come to this particular vertex here, is that we actually create a one particle, one hole excitation. So two of the states, that means this state and that state, remain in the same position. So you could think of this one being the particle state which remains, and this one as the hole state which remains. But then we change the particle hole excitation. So this piece here is giving rise to one particle, one hole excitation. So this is a one particle, one hole type of excitation. And that is not possible with the constraint that we are not going to break any pair. And then the final one, which we have here, this one, is a two particle, two hole excitation. So this state which we have here is a two particle, two hole. So we do an intermediate one particle, one hole, and we have a final two particle, two hole, which brings us back to the ground state. So this is not possible. So this diagram also is not going to contribute. Then we are going to have contributions to third order, which will contribute. And one of them is simply going to be the one where we propagate two particles. This diagram here, which we discussed before the break. So in this particular case, what we could think of is that this excitation, the first excitation which we have, this is a two particle, two hole. But this also is a two particle, two hole excitation. And this again is a two particle, two hole excitation. So the way we could think of this now is that we move in the lower one here from phi 0 to the state phi 1. And here we could now think of going from phi 1 to phi 2. And then at the end here, we go from phi 2 back to phi 0. So if we look at the analytical expression for that specific state, we would get something like this. We would have a phi 0 of hi. We would have a phi 2 here. And then we have a phi 2 of hi. Remember now that the diagonal matrix elements in this specific case are just going to act on the one body part of the Hamiltonian. So the one body part of the Hamiltonian is not going to be present when we take and compute matrix elements between different Slater determinants. And here we would have a phi, so this is a 2 here, a phi 1, and then we will have a phi 1 here of h and phi 0. So this is the way you can think of this. And then we have these energy denominators, which I leave unspecified, squared. So this is one way to think of that specific diagram. And then when you go to fourth order, you will have similar diagrams, which will be 0, and diagrams which will be non-zero. And you have all the diagrams listed in the midterm. So you don't need to draw all topologically distinct diagrams. The diagrams which we have are taken from the textbook of Shavit and Bartlett. And what you need to do then with a Hamiltonian is simply to identify those terms which are non-zero. And the way you can look at it is simply to ask yourself, which one of these diagrams propagate a two-particle, two-hole state or produce a four-particle, four-hole state. All other diagrams, like the one which we saw here, which now creates an intermediate one-particle, one-hole state, or this diagram here, which also has a one-particle, one-hole excitation, they are all going to give us something which is 0. So you have to identify from the diagram the different physical processes. So hopefully this kind of midterm allows you to, one, calculate things analytically, compare these with FCI, but at the same time allow you to build this kind of intuition, which a many-body practitioner normally acquires by many, many years of experience, but where you now can look at the mathematical expressions like we have in this specific case here. And we know that then explicitly these states phi1, phi2, etc., they are allowed. And these would be excitations which you could include. Whereas the one particle, one state you have here is not an allowed state when you don't allow for breaking of pairs. I see that there is a question here. Okay, that was another thing here. Okay. So this is roughly the outline of the midterm. And I hope that this discussion of the various contributions can allow you in getting started. The first part of the midterm is a technical part which deals with you assessing that the Hamiltonian actually commutes with the spin projection operator, so that the total spin projection and also the total spin are conserved quantities. So this is to a certain extent a boring exercise in using the commutation rules. Then we have the next part, which deals with you showing that the Hamiltonian also commutes with a pair operator. So that means that the number of pairs is also a conserved number, a conserved quantity. And then when you have this, you can set up the Hamiltonian matrix, diagonalize it. In the Hamiltonian matrix, you can also run diagonalizations where you leave out the four-particle, four-hole state. That is an approximation to the full configuration interaction theory, which you will often find in literature denoted as CI, configuration interaction, with the singles, which is a one-particle, one-hole excitation, and doubles, which is a two-particle, two-hole excitation. So if you leave out the higher excitations than two-particle, two-hole, you're simply doing a calculation with the singles, which are one-particle, one-hole excitations, and doubles, which are two-particle, two-hole excitations. So this kind of hierarchy of truncations is widely used in full configuration interaction theory, because that reduces the dimensionality of the problem. And then if you take away the four-particle, four-hole excitation, then you can make a direct comparison with many-body perturbation theory to second order. And if you go to third order, you will also have a contribution like this one, which now includes two-particle, two-hole excitations. And then you can compare a truncated FCI calculation with many-body perturbation theory, which then to third order will, in our case, only contain two-particle, two-hole excitations. You have to go to fourth order in perturbation theory to get four-particle, four-hole excitations. So I'm going to stop the recording here.